Welcome to Combinatorics. This is the first lesson in a series of lessons on the topic of combinatorics. In this first lesson, I'll define combinatorics and then I'll give you some examples of the different aspects of combinatorics. And then in future lessons, I'll actually get into more details. Combinatorics is a branch of math primarily concerned with counting, arranging, and combining discrete objects according to specific rules. In the final analysis, what you want to do is count the number of entities in a particular configuration. Now, what makes the problems hard is some of the descriptions of the configuration are not all that apparent as to what the number of entities are that fulfill the particular arrangement. And we'll see a number of examples here. I'll start with the counting principles, which are pretty simple. There's the addition principle for mutually exclusive events. In other words, events where if one happens, the other events cannot happen. And then there's the multiplication principle for independent choices. So let's say you have 3 shirts and 4 pairs of pants. The multiplication principle says there's 3 times 4 or 12 possible outfits. You pick 1 shirt and 1 pair of pants, and there's 12 different ways of doing that. Then the variation on that is, let's say someone wants to give you a gift, and you have a choice of 3 different shirts or 4 different pairs of pants, and you can only pick one out of that selection. So in that case, there's 7 entities from which you can pick one. So there's 7 options in that case. Then the next level of complication are what are called permutations, arrangements of objects where the order matters. So the number of permutations of n distinct objects taken k at a time is given by this formula here. So n factorial divided by n minus k factorial. If you haven't seen this before, n factorial is 1 times 2 times 3 all the way up to n. So for example, 5 factorial is 1 times 2 times 3 times 4 times 5. And I have a simple example here. Arrange 3 distinct books, A, B, and C, so that's the names of the books, on a shelf. How many ways can you do that? So that's 3 distinct objects taken 3 at a time. We're taking all 3 at once. And so that's 3 factorial divided by 0 factorial, which is by definition 1. So you just get 3 factorial, which is 6. Another variation, which I don't have printed out here, but I'll just give it to you verbally. Let's say you have the same 3 books, but you can only take 2 at a time. How many ways can you arrange those? And then it would be 3 factorial divided by 3 minus 2, which is 1. 1 factorial is 1. So again, you would have 6 ways of picking 2 books and then arranging them one way or the other. So you could pick A and B, and then you'd have the arrangements AB or BA, or you could pick A and C and arrange them as AC or CA, and then BC, and you can arrange those as BC or CB. So, I mean, these simpler ones you can just do by enumeration, but you need the formula if you have more complicated arrangements. Next, we have combinations. This is similar to permutations, where you have n objects taking k at a time. However, the order doesn't matter. And this is the formula. It looks similar to the permutation formula, except now you're dividing by a k factorial because you don't care about the order of the terms selected, the items selected. So we have here an example. You have a committee with 4 people, A, B, C, and D, and you want to pick 2 of them. How many ways can you do that? So of course you don't care the order that you pick them in. And I've listed them all here. You can pick A and B, A and C, A and D, B and C, B and D, or C and D. and you don't care whether it's BA or AB. So that's 6. And if you use the formula, you have 4 factorial, 1 times 2 times 3 times 4, and then you have 2 factorial and 2 factorial again. So that's 2 times 2, that cancels out the 4, and you get 1 times 2 times 3, which is 6. This appears, this entity here, this n choose k, that appears in the binomial theorem. So I point that out because we'll see this in some cases. This is from basic algebra, but the combinatorial combination thing appears in the formula. And then we have the pigeonhole principle, which seems simple, but it's sometimes tricky. We'll see it in some problems in future lessons. So if you have n items, n pigeons, for example, and you want to put them in n containers, or if you have more than n items and you want to put them in n containers, then at least one container must hold at least more than one item. So I have an example here. You have 13 people and 12 months in which they could be born. Then from the pigeonhole principle, we know that there's at least 1 month where at least 2 of the people are born in that month. The inclusion-exclusion principle is a method for counting the size of the union of multiple sets by adding and subtracting overlaps. We can generalize this to any finite number of sets. I have an example here for 2 sets. We want to find the number of integers from 1 to 30 that are divisible by 2 or 3. So we'll divide this up into 2 sets. The set A that has multiples that are integers that are multiple of 2 in the range from 1 to 30, and there's 15, right? It's just the even numbers. And then B is the set of integers from 1 to 30 that are divisible by 3, and there's 10 of those. Then the intersection, in other words, integers that are divisible by both 2 and 3, there's 5 of those. They're basically multiples of 6. So you'd have 6, 12, 18, 24, and 30. So, and we want to find the union, either or. So any integer from 1 to 30 that's divisible by 2 or 3. So we have our set A that has 15 elements, our set B that has 10 elements, and then we have the intersection, which we're counting twice. So if we take 15 plus 10, we need to subtract 5, basically the intersection, because it's been added in twice, and we get 20. So that's the number of integers from 1 to 30 that are divisible by either 2 or 3. And as I say, this can be generalized to any number of sets. Even for 3, it starts to look complicated because the intersections are added and subtracted multiple times. So by the time you get up to 4 or 5, you have a rather complex formula to deal with. We have another methodology here, formal power series used to encode sequences and solve counting problems, recurrence relations, and partition problems. So what do I mean by this? Let's take an example. The number of ways to roll 2 dice to get sum k from 2 to 12. So each die is number 1 to 6 standard die. And we can get that from this generating function. So we have x plus x squared all the way up to x to the 6, and then this whole thing is squared. And the coefficients actually give us the number of ways of rolling the different possible values of 2 dice. So for example, we have only one term that's x squared, and there's only one way of getting it 2. That's when you roll 2 ones. Another example would be 7. There's 6 ways of doing that, and in fact, the coefficient for x to the 7th is 6 if you multiply this out. And I also listed here the different ways of getting 7, 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, and 6 and 1. And we have the other combinations shown here, 6s eighths, and so on. The number of ways of getting 12 is only one, and that, again, the only way you're going to get an x to the 12th is when you multiply this times itself, and there's only one way of getting a 12 when you roll two sixes. Okay, so there's other examples of generating functions. I just thought I'd give you an easy example to illustrate the idea. Counting also involves recurrence relations that help us determine solutions to different problems. I have an example here. Perhaps the most famous recurrence relationship is the Fibonacci sequence, which I'm showing down here. The first two numbers in the sequence are 1 and 1. Then you get the next one by adding the 2 before it. And then you get 3 by adding the 2 before it, 1 and 2. 5 is 2 and 3. 8 is 3 and 5. 13 is 5 and 8, and so on. So there's many applications of this sequence. I'm just giving one example of it. Let's have a look at it. The Fibonacci sequence counts the number of ways to tile a 1 by n board with 1 by 1 and 1 by 2 tiles. And I'll show you how it is in this picture here, or at least I'll start off showing. So the first case is pretty easy. There's only one way to tile a 1 by 1 board with when you have your choices are 1 by 1 or 1 by 2 tiles. Then the second case, you can use 2 1s or a tile of length 2. So that gives us 2. So we kind of skipped over the first one here. We have 1 and then 2. Next one is 3, and the way you get this is through the recursion of how these numbers are defined. You put a 1 tile next to each one of these from your previous case. So you have this here and this here. And then you go 2 cases back and you put a tile of length 2 next to that. And that gives you the 3 possibilities. Then you do the same to go from 3 to 4. Where there's 5 possibilities. You put a 1 next to the previous case. So you have a 1 next to this to get this one, 1 next to this one to get this one, and 1 next to this. And then you get 2 cases back. And you put a tile of length 2 next to each one of these. And you get this and you get this here. And then you can just continue the process. So it's essentially governed by or exhibits the Fibonacci sequence. I have a couple of more items here on this slide. So we have partitions and compositions. It's the number of ways to write a positive integer as the sum of positive integers. In the case where you don't care about the order, they're called partitions, and where you do care about the order, they're called compositions. So if we take the integer 5, there's 7 partitions. 5, 4 plus 1, 3 plus 2, 3 plus 1 plus 1, 2 plus 2 plus 1, 2 plus 1 plus 1 plus 1, and then just 1 added to itself 5 times. And we as I say, we don't care about the order here, so we don't count 3 plus 2 and 2 plus 3 as 2 different items in the list. We just count them once. Then you have the other case where you are concerned about order, and I won't list them all, but just to give you an example to make the point, 3 plus 1 plus 1, 1 plus 3 plus 1, 1 plus 1 plus 3 are counted as 3 different compositions. And in fact, if you are concerned about order, then there's 32 ways of writing 5. And you can see that here. This would only be 1, this would be 2, this would be 2 different ways. This one, as we just saw, was 3 different ways. This would be 3 different ways. Here you have even more different ways you can distribute the 2, so that would be 4. And then the last one is just 1 way. And then finally, we have graph theory, which is basically various configurations involving edges and vertices, and that gives us a whole bunch of different counting problems. I give you one example here. if we take K4, which is the fully connected graph with 4 vertices and 6 edges, so you can think of a square where the edges are connected along the exterior, and then you have the opposite side edges connected together, and so that gives you 6. And if you apply that to, say, people, if you represent the associations or acquaintances among 4 people, and we say it's a K4 graph, then that means everyone knows everyone else, and so there are 6 different associations in that case. Okay, so that was the last example in this lesson, and I'm going to go into the details in most of these items in subsequent lessons. So stay tuned.